Kai-FuLee is Vice President of Engineering at Google and the President of Google Greater China. He joined Google in 2005 to start Google's operation in China. Before that, he has many achievements. For example, he developed the world's first speaker-independent continuous speech recognition system. This system was selected as the most important innovation of 1988 by Businessweek. He will tell us cloud computing today, which will surely make great impact in our community.
Thank you very much. It's a great pleasure to be here. So welcome to Beijing. I see a lot of you must be here for the first time. How do you like China? Yes, okay. And what do you see in China? Lots of people, huh? 1.3 billion people. And how many internet users? We just heard 220 million. I actually went out and counted. It's actually 230 million. It's been going up really fast. And in fact, this people theme is what Chinese internet is all about. It's explosive growth with lots of people. So consistent with Google's annual tradition about April Fool's Day, this year we decided to do a people-oriented April Fool's Day just for China. So a few weeks ago, we announced in Google China, we're going to, in order to save electricity, we're going to shut down all our servers and we're going to hire 25 million people to do our searches for us. So this actually got a lot of fun. A lot of people thought it was really funny. And we also got 1,800 resumes. I'm not kidding. This is really a lot of fun to work in China. And in fact, this theme is really about people. It's about growth. 650 million people joined the internet since 2000. Almost a third of them came from China. And these people are from everywhere in the world, particularly developing countries. And today, there are about 235 million people on the internet in China, and that's really phenomenal. What do these people want? Today's internet is actually kind of frustrating. I think people want more accessibility. They want to be able to get on the internet anywhere. They want to share content. You know, creating is easy. Creating a web page is easy. Saving it is easy. Sending email is easy. But sharing my photos with my friends, but not others, is not easy. People want freedom. They want to have their data anywhere they are. They want things that are easy to learn, easy to use. And they want, of course, all of that data, especially their own data, to be secure so they're not lost or they're not seen by unwanted parties. And that brings me to the topic today of cloud computing. We believe at Google, and I think at a lot of companies, that cloud computing really solves a lot of these problems. Now, to be sure, cloud computing is not new. It's certainly not Google's invention. We're just a part of it, like all of you are. And I think there's a number of really important attributes of cloud computing. Some of them we don't really notice, but day by day, it's changing the way we use the internet. I think there are 4 key attributes. First is that data is stored in the cloud. The cloud is defined to be some server somewhere, not necessarily known by the user, so it's abstracted, but it's there and it's dependable and it's accessible. 2, software and services are increasingly moving to the cloud, and that they're accessed through the web browser. So that also implies the client computer should be something that really supports a full-featured web browser. And when I say client computer, I should correct myself and also say phone, television, cars, or any device. So anything with a web browser ought to be able to run applications in the cloud. Third, we believe it's important that we build these standards and protocols that are open. So for example, Linux, Ajax, and LAMP are some of the examples that, thank you, that we at Google like very much, and I know a lot of you like. I want to also remind you of some really magical moments. I remember the first time I saw Google Maps, and I thought, no, that can't be. It can't really be. This is not a web page. This is not, web page should be text. But here is a draggable animated map. How is that possible? Well, this was with Ajax. And many other such open standards and technologies are making more and more web-based applications access through web browser more and more lively and useful and interesting. And the last one really important is that it should be accessible from any device, especially phones. We've heard about the number of phones in China and in the world. And I can share with you that as the Apple iPhone hit the market, our backend servers really noticed, even though the iPhone shares are not large, but on a per phone basis, the web usage is about 15 times more than other web-capable phones. So this power of data stored on the cloud, a very good client machine that runs the web browser, can accessible from this great device, can really dramatically increase the use of internet on the devices connected to the cloud. So this is probably something well known to all of you, so I'll go pretty quickly. We all know that the PC era started being very hardware-centric. You have your machine, your disk, your memory, your CPU, your applications. And then it moved to the client server, where you write programs that are stored on a server that can deliver to many clients. And that was great for enterprise computing. And what cloud computing does is it abstracts that server and moves it anywhere and makes it very scalable. And that essentially abstracts and hides the complexities of computing. And that's really important for not just users, but also IT professionals. Remember, about 1,000 years ago, people in China stopped putting all their money under their pillows and started going to banks. And they trusted their data to the banks, which were at that time more client-server, and then over time, banks became clouds. We can go to any ATM and withdraw money. Similarly, about 100 years ago, people were still having generators to generate their own electricity. And eventually that became centralized. And none of us care when we plug a computer into the wall where that electricity is coming from. It just works. And I think the notion that it just works is what cloud computing is all about. Clearly, there are a number of well-known driving forces that's making possible this utility-like capability of cloud computing. Falling cost of storage, ubiquitous broadband, especially with the Wi-Fi, WiMAX, 3G, and other standards, and democratization of the tools for production so people can create their own content. These are beginning to make this cloud-based computing more and more like utility. And these ideas, to give proper attribution, since this is an academic conference, really is due to IBM and Digital Equipment back in the 90s, who proposed that more and more computing should become like a utility. But at that time, these three key factors and forces were not in place. So it's really today that we're seeing this dream realized. And let me now talk about, in addition to those three key things, I want to talk about 6 additional breakthroughs that will make cloud computing even more exciting for all of us in the coming decade. Well, the first one is user-centric. And that's what cloud computing really is all about, is that the data moves with you. The application moves with you. It's not the machine. It's not your one PC that knows about you. And that's what the users want. They don't want to reload their address book. They don't want to have to reload their applications and keep them all up to date. And that's really very painful. And I think we only have to think, A, how bad do we feel if we dropped and broke our laptop? Pretty bad, because all your data is probably gone. But with cloud computing, it will be properly backed up. And how easy is it to switch a cell phone? Very hard, because the contacts are hard to do. If anyone still believes that we can manage many devices and have them synchronized with each other, I only ask you, do you ever use that infrared feature that you have probably on your PC that can sync with other PCs? I don't think any of us use that. It's just not convenient. It's just not user-centric. So increasingly, I believe data will be stored in the cloud. It will follow you wherever you are. So in the picture shown here, your photos, your preferences, your calendars, your emails, your phone, music, your news, your messages, all stored in the cloud. And whatever device you happen to be on, it doesn't have to be your computer. It could be a brand new computer you just bought. It could be a brand new cell phone that you just got. Once you're connected to the cloud, it's yours. That device becomes yours. And that magical process makes it user-centric and very usable. And not only is it yours, but you can also share it with others. You can do things like photo sharing. You know, in the past, we used to use analog film and put it in, at best, put it on a digital CD, and it gets filed away somewhere. But nowadays, we may have a completely digital process. But what's even more magical is if you use something like the Picasa Web, your photos can be put on the cloud. You don't know what server, it's accessible anywhere. You can download it to your iPhone, you can show it on your PC, you can put it on your TV, you can print it, you can make merchandising out of it. You don't have to ever worry about where that is. And I know we're not quite there yet, but I think increasingly, the moment that I can feel, hey, I don't have to synchronize my 10 copies of my photos of my family and work and all kinds of things, and I can set it for myself and share it with others with proper protection, that will really change, again, the way we deal with photographs, much like the digital camera has done already. Another example is using email, using web-based email, such as Gmail. If you just have a web browser and you log in, it brings you to your email. And what's really great about that is, of course, you can use it on any device. It's a large amount of storage that you're maybe even more than you can afford on your local drive. And that any new device you have, even if you go outside, let's say at a conference where public terminals are provided, or in an internet cafe, you can still check your email. I think this is nothing new to any of us in this room. And I think sort of, if anyone still doubts, privacy and cloud, is this really going to work? I would bet everyone in this room has some kind of a cloud-based email. So we are already implicitly entrusting our most private data to this magical cloud. And it's working great, and as we have more devices, the power will even be more amplified. And mobile devices would be another very important area. Today we go through the internet, the browser, the search engine, and through which it becomes our window to the world. But we're not on our computer all the time, so mobile options makes that even more powerful, because a mobile phone is with you anytime, and it probably knows more about you, and it knows where you are, and that GPS will give you even more targeted content that you want from the web. And in China today, there will be 600 million cell phone users, and worldwide, by next year, there will be 3 billion cell phone users. So that's going to dwarf the number of PCs that are internet accessible. And I think when we talk about the data follows you, it's user-centric, the arrival of the mobile era is going to make that attribute all the more powerful for all of us. And what do you do on a cell phone? Actually, a lot. You might think, oh, with a small screen, there isn't much you can do. But in this case, when we search for Iraq, it will give you breaking news on the top of the page, and you just need to scroll down. And if you had an iPhone, that would be really easy. And it will show you more results from the web. And if you go further down, it will start to be smart and know, oh, you're in New York. Let me tell you some Iraq news agency that happens to be near your vicinity. So all of these results can be combined and delivered. And the most powerful, most popular application that we have seen on mobile devices is maps, because people get lost, because spontaneously they want to go somewhere. And when we think maps, it's really no longer like the traditional flat piece of paper that shows you where parts of the city is, but it can allow you very advanced functions, such as searching nearby, delivering real-time traffic. In Switzerland today, actually, you can track exactly where a train is that you're waiting for. And increasingly, that real-time flow of information And then the combination of these so-called mashups will provide even more power. And when you call something, and the map itself is really a misnomer. The capabilities are really enormous around these kind of mobile capabilities. And this we really need to have with us all the time. And as we went from relatively static content, like your data, into photos and email and maps, we see that this is not just about putting your data in the cloud, but the application is running in the cloud. When you use something like Google Maps or search, most of the computation is running in the cloud. And we're increasingly seeing that shift. And we'll talk more about how to make that economical later. And the last example I'll share is with a set of old products and some new products from Google. The Google Docs allows you to create documents. Google Page Creator allows you to make web pages out of them. And we came up with a new product called Google Site, which basically says, hey, for small teams, it's a real pain to have to buy your server and rent server space and buy bandwidth. Why don't we just host it all for you? And that was really popular, so that a small team of people at no cost to them and no hassle at all within an hour can put up their own website that's hosted by Google. And I think other companies may well do similar things. Within the first few hours, 50,000 sites were set up. So that it's going to be very, very popular capability. And again, that allows you not to just to access the data, but to create it anywhere. And this picture shows you the site that's completely developed in the browser. So earlier when I said cloud computing is about just opening your browser and staying there. Here we saw Google Docs running in the browser, Google Page Creator running in the browser, and creating content hosted on Google Site, again viewable by the browser. So the browser is, in fact, the platform. The second part I want to talk about is task centricity. Now, what's a task? Well, a task is something I want to accomplish. I want to work with my fellow teachers to create a curriculum. I want to work with my fellow high school students to create our project. That's what people really want to do. People don't really want to say, I want to do a spreadsheet. I want to do draw a picture. People really want to solve a task. Yet, in the past, when there wasn't a cloud-based distribution of the digital bits and the applications had to be delivered every few years in a shrink-wrap package. So it's not possible to build a product that says, this product is for the task of teachers who want to collaborate on the curriculum. Nobody can ever make a profit like that. But today, with cloud computing, the so-called applications of the past, the spreadsheets, the word processing, the presentations, all become modules, and they can be composed, and also email and calendar, and they can be composed properly and laid out on a very task-specific manner that solves the very problem you want to solve. So as an example, here is an email that a teacher might have sent to his or her colleague. The email says, hey, we need to finish our curriculum by tomorrow. Please go to departmental curriculum, which is a hyperlink to a URL to a web page, and finish your section ASAP. And let's all meet there at 6 p.m. for discussions. Well, what does meet there mean? In this case, it means the web page. So I think the metaphor of a web page will become increasingly not just a page of text and multimedia, but a place where people can collaborate, share, congregate, discuss, solve problems, and complete their tasks. So when you actually click on that departmental curriculum, you're taken to this page, which has what looks like a spreadsheet on the left. But what's interesting is what's on the right. It shows you the number of people that are viewing this spreadsheet. And you can see there are 3 people viewing it. And each of them can make changes in the spreadsheet, and they can collaborate. And then when they have debates, for example, if one teacher says this course should be 4 credits, and another teacher disagrees, they can jump in and have a chat in this window and talk to each other. So just virtually on a web page, a task can get completed. And we think the power of cloud computing will allow this kind of capability to move beyond applications into real tasks. And we think communication is a task. That's why Gmail is not just a mail client. So within Gmail, you'll see a chat history, quick contacts, you can chat within Gmail, and you can have pop-up chat. So pretty much it allows you to mix real-time and non-real-time, store and forward, as well as in zero latency kind of discussions. And it's all combined in a one task, because people think, I want to communicate this message with that person. I want to discuss this topic with that person. Email is just one means of doing so. They happen to be online, why not have a real-time discussion? So that kind of a rich communication task is increasingly going to be possible on the internet. And we saw this example where people can chat and communicate about a spreadsheet. Here's another example where people can collaborate, and you can invite specific people and specific groups. And in fact, all of these web-based documents are merely URLs, and they are automatically version controlled. So you don't have to worry about, oh, if you did something wrong, then go roll back and go back to yesterday very easily. Also, you can publish very easily, not only to the whole world, but also to a select group of people. So we think these kinds of task capabilities are going to be increasingly powerful and customizable. And of course, you can organize all of your common tasks. Why accept anybody's homepage? Why not create your own homepage? Why shouldn't your homepage have the very tasks that you care about? Why should you create all these tabs and favorites and go to them one at a time? Why not put it all together? And that's where a product like iGoogle comes in. Here we have consolidated the key tasks that I personally am interested in, the key blogs that I want to watch and subscribe to, the key news, the areas I want to watch for, my Gmail, the weather in my city, and so on. Why not make it task-centric so as to save time from us having to run applications serially? The third great thing is power. And this really goes without saying that when you have lots of computers available on the cloud, it can do things that your PC cannot do. So a very simple example is Google Search. Do you find Google Search to be faster than searching in any application like Windows, Outlook, or Word? I would hope so. 0.1, 0.2 seconds. And that's not to say anything bad about people who make those applications. I think actually a very key reason is that Google uses not one computer, but lots of computers when you do a search. And if you're searching within Word, you're just using your computer. And well, think about building a search engine. Can you even build it on one computer? So hypothetically, let's say there are 100 billion web pages, 10 pages, 10K per page, and there's 1,000 terabytes of disk. Now, where can you buy one of those? You can't. So there are tasks that are really impossible to do with one computer, or even a very powerful computer. You simply have to figure out a way to harness the power of parallel computing on the cloud. And the cloud computing should have at its disposal essentially an infinite amount of disk and an infinite amount of computation. And as long as they can be parallelized, the speed of what you want to do will be faster. So using the search example, we see here that actually when you issue a query to a web search, it's going to ask thousands of servers, some of which are doing indexing, some indexing servers, some of which are actually serving up documents. So every Google search is using at least 1,000 machines. And that's something you can't possibly do on your own PC. And of course, it's accessing thousands of terabytes, which you can't do on one computer. So the cloud computing is not just moving computing from your PC to something far away, but it's adding a lot more power and capabilities. And one of the key things Google announced last year was universal search. This was at an event called Searchology. The basic idea here is that with traditional web page search, it's not very diverse. It's largely doing information retrieval using hints about word matching and TF-IDF and PageRank. But it doesn't have much more knowledge. People quickly found that if you want to do news search, scholarly article search, image search, restaurant search, the web search isn't necessarily the best way to do it because the ranking signals are different. So a lot of so-called vertical searches emerged, and they each do a better job than the web page search in delivering accurate results. However, it's very complex, and people have trouble remembering where to go to when they want to find something. So the idea of universal search is quite simple from a user point of view. It's merely saying, let's build one search that will search all of these vertical searches. And let's make it all work within one box. And that search will access lots of data behind it. For example, if you search for a particular scandal about a photo of a tiger within China, you will see here it's got news about the scandal and the photos of the tiger, as well as lots of other information. If you search for a stock, that's the name of a publicly listed company, it will show you the stock graph, the latest price, almost real-time pricing, as well as news, as well as other content about that publicly traded company. And if you do our favorite search, George Bush is funny, you will actually see YouTube that can be played from within the search results with lots of funny George Bush moments. Now, how does all this work? Now, in this talk, I can't possibly explain all the details, but in short, it's a search that's simultaneously querying and searching over all the databases of the web, news, image, video, so on and so forth. And there can be tens of such sources today, and there will be hundreds and thousands in the future. And that is going to require the power of cloud computing, because it's lots of these searches going on simultaneously, and then they get ranked by one overall ranker. And that's even much more compute intensive than the web page search itself. Other technologies that will result in intelligence. I have worked on speech recognition for a long time, and Google has worked on search for a long time. And I can tell you, whether it's one field or the other, a ton of data is a lot more valuable than an ounce of algorithm. So cloud computing allows us to collect enormous amounts of data and then using machine learning, statistical methods to come up with insights and to potentially solve previously impossible problems. So I'll just give you an example. I'll use machine translation as an example. So how does that work? Well, Google already crawls the web. So we have a team at Google that is crawling all Chinese text, all English text, and all bilingual text. And overall, there's more than 1 trillion words collected. And from this trillion words, we want to learn orders of words and also mappings of words. So what's a mapping of words? Well, here's an example. Xinhua News Agency always professionally translates its news release in many languages, including English and Chinese. So in this case, we feed our learning algorithm lots of data, one of which is a bilingual feed that says, we know because Xinhua News Agency told us so, these two articles mean the same thing. So we ask our machine algorithm first, can you align these two articles sentence by sentence? And you see the colors here delineate sentences within the two translations, and the colors match each other. We have the algorithm say, well, let's take one sentence pair at a time, an English-Chinese pair, and see if we can align the words together. So in this case, the two sides matches 双方, discussed matches 讨论了. The latest development jumps over to the end because the grammatical rules of the two languages are different. to最新发展. Of goes to the in the middle. Situation goes to 局势, Middle East goes to 中东, and the really hard one, period, goes to period. So that allows us to extract phrases and then align them against each other. And then we collect statistics. As an example, let's take as in this sentence, latest. Latest in Chinese could be 最新 or 最近. Could be either one. It really depends on what, 或者最晚, right? So latest could be actually mean the newest in this case. Latest could also mean really late. It's very strange use of, very ambiguous. So what we learn here is we collect statistics of all the alignments. How often is latest mean the newest? And how often does latest means the latest, like the last is in chronologically. And we collect certain statistics. But to make it smarter, we might say, well, latest development, does that particular phrase usually mean the newest or actually the latest? And we'll learn the proper statistics so that latest development will be translated to 最新, latest arrival will be 最迟 or 最晚. So those actually map to different things, and as we have context, the translations can be more and more important. So we do all this work over 1 trillion words, and we can tell from the right graph that as we add more training data, the translation quality improves. So that proves the point I made earlier, that more data plus more analysis leads to intelligence. And the left picture shows at the National Institute of Standards and Technology competition, the Google translation came out at the top. So of course, translation is no fun to talk about without seeing some examples. So here I have an example. This came from the Supergirls competition, which is the Chinese idols, if you will, very similar to the American TV show. If you run it through our translation engine, which has all the statistics collected from the 1 trillion words and applied properly, the most likely outcome is Supergirls 5 finally settled after a heated rivalry. Fei Xu shed tears at the stage. So it's not perfect, but largely you understand what this is about. And if you're unhappy with this translation, you might want to look at another translation engine, which shall remain unnamed. Ultra female Wu Qiang passes through the intense contention, finally thus to fall decides. Xu Feilei sprinkles the stage. If you actually know Chinese and compare word for word, what the other translation engine did was they took each word and translated it literally. It didn't consider context, such as the example of latest that I mentioned before. Of course, we don't claim Google Translation solves the translation problem. We think it's very useful for people who run across a language that they don't know. They can get a gist of something. And we think, we basically say it's approximately high school level translation quality, which means for most Chinese people in the audience, you probably know more English than Google Translate. But for a lot of our American or European visitors, when you run across a Chinese website, you have no other means, so Google Translate is a pretty good choice. We really don't claim it's any better than human beings because it isn't. Not as good as professionals, it's not even nearly as good as someone who's bilingual like myself. But there are some interesting cases where Google Translate can beat humans. I found some interesting photos on the internet, which might help the foreign visitors as you wander around. So if you actually see a humanly translated photo, sign in a supermarket that says small food, that means snack. And if you see patrol to sign everywhere, don't worry, they're just signing in. They won't sign on you. And if you see a time sexting, don't run away. This just means disposable products. And my favorite one, if you want to buy some dried fruit, do not be offended by this sign. All right, enough on machine intelligence. This session is about people, so let me talk a little bit about another way to get intelligence. Lots of data can be processed by machine analysis, like in machine translation, to generate intelligence. It can also be combined with humans, with collaboration, with contributions, to turn not something that's just a mess of photos into a very powerful tool. I saw people talk about Wikipedia. I think that's a great example that people combined together creates intelligence, or at least creates knowledge. And in this case, Google Earth is another very interesting product. Now, I think most of you know about the basic combining maps and satellite imagery and aerial photos into a very cool stitched flyover experience. But that's really not terribly useful in itself. It's only useful when people can contribute. It's only useful when National Geographic can take their photos of the African wild animals and put high-res photos in place on Google Earth. It's only useful when creative people can do all kinds of things, such as real estate information, traffic data, restaurant review, news, 3D buildings, and so on, to really turn a tool from just a bunch of pictures into, in this example, the National Weather Service in the United States allows people to visualize the cloud formations around the world. And this flips Google Earth upside down to look up at the sky and really helps teachers teach astronomy. And this gives you lots of detail of locations. And this allows you to superimpose artificial or 3D buildings on top of satellite imagery. And I think it's that capability that unleashes the creativity and imagination of all the web users that brings knowledge and intelligence into an application that fundamentally is a data-centric application that merely zooms over trillions of pictures and makes it all work well together. But it's really the power comes from lots of other people. So the intelligence is the other part that comes from the power that's offered. But now you might wonder, oh my goodness, this machine translation and Google Earth and Google Search and Universal Search, that must be using a lot of computers and that must be really expensive. But actually not. One of the interesting findings that we found at Google is that, yes, you can go out and pay $42,000 for a server and buy 1 million of those and bankrupt any company on Earth, or you can actually buy a really cheap computer for a fraction of the costs. And if you do apples-to-apples comparison, you can really get at about 30x difference if you went to really cheap computers. Okay? Ignore the details. The numbers may be a little bit old, but I think a high-end, fault-tolerant, multi-processor, multi-disk array machine can be 30 times more expensive than the cheapest server you get. And we at Google think, forget about a high-end machine, just buy the cheap server. That will save you 30x the price. Now you would of course ask, what happens when the machines go down? And surely they will go down. If we assume you have 20,000 machines, and if we assume a machine fails a few times in a year, that means in your 20,000 machine cluster, that's 110 machines in a year that doesn't work. You can't just go tell the Google Earth user, sorry, you can't fly over Africa today. Our machine is down. Or the Google search user, oh, no searching of images. So of course that won't work. And Google's solution is, we think a lot of faulty hardware can be saved by a very powerful software layer that automatically replicates and automatically allocates tasks to these machines. So I'll get into a little more of that later. But let me tell you the progress we've made on the hardware side addressing the costs. So the 30 times cost is just a commercial figure between two existing products. The actual numbers at Google may be even larger because we really go through the extra mile to save every component we can. And we actually manufacture a lot of servers. It's just that we use them ourselves and we don't sell them on the commercial market. This revelation really came by when Larry and Sergey started Google, and they got a bunch of very cheap hardware to build the first Google server in 1997. And those cheap servers they borrowed from all kinds of places, of course, went down a lot. And that was what gave them the inspiration. Why don't we build a software layer over cheap, unreliable hardware and see if the collection of machines can be made reliable? So in a short period of 2 years, engineers at Google created what looks like this server. Of course, they made a terrible mistake. They put all the wires in the back of the machine. So every time anything needs to change, you have to turn the whole thing around and maybe shut them all down. And people at Google learned quickly. So in 2000, you can see on these servers, the wires are now in front. But we didn't realize how many machines we would pack into a room. So we had to install a special cooling unit here, also known as a fan. And we eventually fixed that problem. And about 2001, we had the capability of turning a new data center up and running within just 3 days. And this is our most current design. It's all in-house design based on PC-class motherboards with low-end storage, networking hardware, running Linux, and in-house software. So we have accomplished the affordable design. And now, how does all this software work? And I'm sure many engineers and developers in the audience are asking the questions, well, with all these flaky servers, how do you provide a non-flaky service? In other words, can you do a distributed disk storage that's fault tolerant? In other words, store your files in lots of servers so that when one dies, there's still copies elsewhere, and it's smart enough to replicate and become fault tolerant. Second question is, well, to run some of these tasks, such as holding every web page from yahoo.com, well, that's a huge amount of content, but that's accessed a lot. So maybe we should keep it in memory. Well, no machine can take that much memory. So essentially, you need to have lots of servers that have a distributed shared memory that might be thousands of terabytes in size. And the third question is, well, how do you program this thing with distributed storage, distributed memory, and how do you program this thing? Especially if we don't know if there's 1,000 servers or 100,000 servers. You'd like your tasks to be scalable. The more servers you have, the more parallel you make it, right? And then as machines die, it ought to still work. So these are the three key questions. And I'll just give you three brief intro to the ideas we have, and you're welcome to go to Google Labs to get more details on the actual papers. So in terms of fault-tolerant distributed disk storage, our approach is that every piece of data is replicated 3 times upon failure, and then they're stored in these chunks. So you can see in this picture that C5 is replicated in the chunk server 1, 2, and N. And let's say one of these chunk servers dies. What happens? Well, the master will notice that one of the chunk servers died, and it will create a new server and redistribute the chunks so as to maintain always 3 copies of the data. And Google actually has more than 200 of these clusters, the largest of which are as large as 5 more petabytes of disk, distributed over 5,000 machines. Second question about distributed shared memory. We came up with a technology called Bigtable. It's a distributed, persistent, multi-level storage of very large tables. And the rows and columns are the abstraction of storing data. And it supports very basic database operations. It's not a full database by any means. You can see on the bottom that the table is cut into tablets, and the tablets are stored on individual machines. And some of the largest cells can be as large as 700 terabytes and distributed over 2,000 machines. And these, again, are problems that if you just had one PC or a bunch of servers, it's really not possible to solve the web-size problems that we're likely to increasingly run into in the world of cloud computing. And lastly, how do we program this thing? The approach is called Mapreduce, and the basic approach is we assume that you have a computation that's repeated over a large amount of data, let's say 1 trillion records. And the idea here is you cut the 1 trillion records, let's say you have 1,000 machines, you cut the 1 trillion records into 1,000 parts. Each of the machines will load 1 billion records, and they will simultaneously run the same program over these billion records. And they will have a way to checkpoint and synchronize their results, and eventually it's reduced to that result that you want. For example, if you had 1 trillion web pages and you want to count how many times does the word conference occurs, or if you want to count how many images there are, to do it 1 record at a time will be prohibitively expensive. And Mapreduce allows you to cut it into thousands of parts and execute them separately, and then reducing back into a single answer. So just to show you how often Mapreduce is used at Google, in 2005, there are 72,000 jobs. And then in the September 07, there are 2 million jobs of Mapreduce being run. And you can see that we in the company are increasingly figuring out more and more types of computation that can be decomposed into Mapreduce, and it's saving us lots of time. There are projects that could take a month or a week are now taking a few minutes or at most hours, and that's saving us a tremendous amount of time. Now, not everything is suitable for Mapreduce. Since I'm from Google China, please indulge me to talk about one technology from Google China that cannot be solved by Mapreduce. And this is an example of trying to parallelize support vector machines. And similarly, doing things like singular value decomposition require matrix operations. And matrix operations cannot simply be cut into 1,000 pieces and operated on separately and then glued back together. So our researchers have come up with a way that doesn't solve the problem completely and perfectly, but approximates it quite well. And this technology is published at NIPS December 2007, and actually the open source of this program is available at code.google.com. To just give you an idea, what is the problem we're trying to solve? Imagine you have a trillion by trillion matrix, and you want to derive a 1,000 by 1,000 matrix that approximates the trillion by trillion matrix so that you can do further processing on it. But even with our current capabilities, storing a trillion by trillion and processing is very difficult on our existing infrastructure. So what we actually do is we first turn the trillion by trillion into 1,000 by trillion by using what's called an incomplete Cholesky factorization. And then we can parallelize that computation. And after this process, we do it by trillion by 1,000, and then 1,000 by trillion, and then we do a matrix product that eventually ends up with the 1,000 by 1,000 matrix that can be roughly thought as the eigenvectors equivalent or the singular value decomposition-like process that gives us a much smaller matrix that we can much better handle in the future. And this kind of capability gave us very similar to Mapreduce kind of speed up. We were able to take a task that took 5 days on one machine to something that takes only 40 minutes on 250 machines. And Edward Chang and his team that did this work is at the conference, and if you want to learn more about it, please feel free to speak to him. But overall, these kinds of technologies, we introduced 4 today, and I'm sure there are many more that will be invented by all of you, really tells us we're getting ready for an amazing era. An era where the programmers' capabilities can be amplified more than ever before, where their creativity can be unleashed to harness not one machine, but thousands and tens of thousands of machines. And it also means new skills are needed, that PC-centric programming skills are going to be less important, and distributed parallel programming skills will be more important. That one server, one application model will evolve towards browser-based parallel application model. And that technologies I introduced, plus LAMP, Linux, and Ajax, and many others will be really, really important. And in order to help people better understand cloud computing technologies and how to learn to program 100,000 machines, IBM and Google partnered together to create a set of university programs, starting with the University of Washington, and we're scaling to many others. And I'm pleased to announce that these activities have also been brought over to Greater China. We have helped create a cloud computing course at Tsinghua, and we're now scaling to other mainland China as well as Taiwan universities. And in the Tsinghua course taught in 2007, it was called Massive Data Processing, and Google engineers as well as Tsinghua faculty taught Mapreduce and other technologies to the students. They came up with a lot of very clever projects, and what's shown here is massive data processing to simulate the operation of the solar system. And if you have any doubt about the power of parallel computing, just think about the 18-year-old Lithuanian engineer who created the largest prime database of all the prime numbers in the world. Or think about when this course was taught at University of Washington, one student worked on the projection of collision between the Andromeda and Milky Way. And these are not just web-based problems. These are scientific computing problems that used to be difficult or impossible, that with the power of cloud computing will become possible. So the cloud computing clearly brings the engineers and developers the capability to harness a lot more computers and unleash their creativity. It also brings users the benefit that they find everything, their PC, their cell phones, their data, their photos, their email, just works. It will certainly change the way we work and play. We also will find, we didn't talk much about this, but imagine an IT shop, an IT professional at a company who's spending all the time dealing with spyware and malware and installation and different upgrades today and compatibility and solving user problems. Imagine when all they have to do is put a browser on each desktop and they can outsource their IT to a trusted shop that's very good at outsourcing IT. It will become simple, it will become safe, because that shop is going to be more equipped to deal with security attacks, denial of service attacks, malware, and so on. The entrepreneurs who want to start their own company and change the world, they will get an opportunity from paradigm shift. They will not be constrained because there are markets occupied by large companies. They will not have to suffer being the smaller player trying to get their voice known. Every time there is a paradigm shift, just like as the internet first wave came along, China saw Sina, Sohu, Tencent, Baidu, Alibaba, all these companies came up. In some sense, these are cloud-based companies, and I think there will be more, because in a paradigm shift, especially one that's powered by open technologies, everybody will have a shot. And government, countries, companies will all be able to leverage this innovation-enabling platform. The capability of having an incredible back-end that allows people to very productively program tens of thousands of machines and deliver useful services will be a catalyst that will help companies become successful. For example, venture capital. Last year, just in internet-based companies in China, $540 million have infused into China. And much more will happen as people see that cloud computing provides a very unique, innovative, enabling platform. And governments will see that it will be a great catalyst of rapid economic growth. So cloud computing is here. You are the stewards of the web and the pioneers in the internet. You're the ones who will make sure that this cloud computing revolution goes forward, and I look forward to working with you on it. Thank you.